Welcome to The Explainer. Today, we're diving into something absolutely mind-bending. We're going to take warp drive out of the realm of sci-fi fantasy and pull it right down into grounded, modern physics to see how real it actually is.
Okay, let's just dive right into this. 25 trillion. That massive number right there, that's the distance in miles to our nearest stellar neighbor, Proxima Centauri. And it perfectly illustrates the ultimate hurdle we face with interstellar travel, the absolute tyranny of distance.
To really wrap our heads around that massive gap, let's think about Voyager 1. This is our fastest probe, zipping through space roughly 19 times faster than a rifle bullet. But even at that blistering speed, it would still take Voyager 70,000 years to cover the distance to Proxima Centauri. Think about that for a second. Our entire recorded human history, from the invention of writing 5,000 years ago, way back to the very first cave paintings 40,000 years ago, that whole stretch of time fits into just a tiny fraction of this one single voyage. Crazy, right?
We clearly cannot just chemical rocket our way out of this problem, which brings us to Section 1, the warp drive loophole.
So, what are scientists actually doing? Well, they're looking at a fascinating little loophole in Einstein's field equations. You see, Einstein's rule says that matter cannot be accelerated to the speed of light, period. But it doesn't actually say that nothing in the universe can exceed light speed. So while physical objects can't move through space faster than light, space can move. In fact, we see this every single day with the expansion of the universe.
All right, so how do we actually build a mechanism out of that idea? Back in 1994, a physicist named Miguel Alcubierre basically mapped out the ultimate cheat code. It goes like this. Step 1. You contract the space ahead of your ship. Step 2, you expand the space behind the ship. And step 3, you literally just sit inside and ride that resulting wave of warp geometry. The wild part? You aren't actually moving through the bubble. It's kind of like, imagine a raisin sitting inside rising bread dough. As the bread expands, the raisin moves along with it. But the raisin itself isn't doing any of the walking. The space around it does all the heavy lifting.
Now, here's the catch. To make this bubble work, Alcubierre's math required a very specific fuel known as exotic matter, or negative energy. This is a theoretical substance with a negative mass density. It basically exerts anti-gravity, meaning if you dropped a chunk of it, it would literally fall upward. It curves space-time outward instead of inward, which, mathematically speaking, is exactly what you'd need to hold a warp bubble open. But we run into a massive problem right out of the gate. Alcubierre's original math, it required an amount of this negative energy equivalent to the mass of the entire universe. Obviously, that's a non-starter. But physicists didn't give up. They spent decades tweaking and optimizing the geometry of the bubble. By 1999, a researcher named Van den Broek got the fuel requirement down to the mass of Jupiter. Huge improvement. And then, by 2011, NASA's Harold White widened the bubble wall, reshaped the whole thing into a torus, or a donut shape, and dropped the requirement down to just 700 kilograms. That is roughly the mass of a small motorcycle. Talk about an optimization win. But assuming we could even find 700 kilograms of a substance that probably doesn't exist, going faster than light brings up some terrifying physics. Let's look at Section 2, the hazards of FTL. When you actually push past the speed of light, this theoretical bubble creates some absolutely catastrophic problems. First off, you hit what's called a causality horizon. That means the ship is literally outrunning its own signals. You lose all steering, you lose the brakes. You essentially become a completely blind, unsteerable ballistic projectile. Oh, and if that wasn't bad enough, you also have to deal with time travel paradoxes, incredibly lethal Hawking radiation, and these destination-sterilizing debris beams. It is a nightmare scenario.
Let's actually zero in on that Hawking radiation for a second, because the front of a superluminal or faster-than-light bubble is moving faster than light itself. It generates its own event horizon. And just like a black hole, this horizon spits out Hawking radiation. But unlike a massive black hole in deep space, this radiation is trapped entirely inside the tiny little warp bubble with you, which means it would roast the crew at temperatures hotter than the surface of a star, basically instantly. Yikes.
And let's say the cruise somehow miraculously survives that. The destination won't. Interstellar space isn't perfectly empty. It's full of stray dust and hydrogen atoms. A faster-than-light bubble acts like a cosmic snowplow, sweeping up all this matter and trapping it in its leading edge. So when the ship finally arrives and drops out of warp, All that accumulated supercharged energy gets released in one unbelievably concentrated beam. Put ominously, the ship survives the arrival, but the star system in front of it, completely vaporized. It's literally like arriving at a peaceful diplomatic meeting and firing a loaded howitzer.
Clearly, faster-than-light travel is just completely riddled with impossible physics and horribly lethal side effects. But don't lose hope just yet, because we are bringing this back from the brink of impossibility. Section 3, the subluminal breakthrough. This brings us to a really crucial fork in the road. On one side, we have superluminal warp. Faster than light, requires impossible negative energy, and, as we saw, creates deadly horizons. But on the other side, we have subluminal warp, slower than light. And in 2024, researchers at a lab called Applied Physics actually published a constant velocity subluminal warp solution that uses ordinary positive energy. That means no exotic matter required, and it's perfectly safe for the crew. And this perfectly illustrates why subluminal drives are an absolute game changer, even if they don't actually break the light speed barrier. You see, because the geometry of the warp bubble is handling all the physics, the crew's bodies don't register any inertial forces whatsoever. A warp ship could accelerate from a dead standstill to near the speed of light, and the crew sitting inside would feel like they were just chilling on a park bench. No crushing G-forces, nothing. Think about what that actually means for human astronauts, say on a mission to Mars. Right now, a conventional chemical rocket takes about 6 months of coasting to get there. Why? Because if we sustained high-thrust acceleration the whole way, the intense G-forces would cause the crew to black out and, well, die. But inside a subliminal warp bubble, space is flat. You can sustain massive, continuous acceleration for days on end without the crew feeling a single thing. It completely transforms a grueling, multi-month deep space transit into a quick, comfortable little trip. Now, you might be wondering, how did they figure this out? Well, this modern breakthrough was largely made possible by a brilliant software tool called Warp Factory. It basically allows physicists to instantly visualize all their complex mathematical designs. In the tool, blue represents positive energy, ordinary matter. White is the vacuum of space, and red is that impossible exotic negative energy we talked about earlier. With this software, researchers were able to systematically tweak their models, running thousands and thousands of simulations until they completely eliminated all of that unphysical red matter from their designs. So the math actually works with ordinary matter. That is huge. But how in the world do we actually build one of these things? Let's look at Section 4, a realistic mission timeline. To get there, we really have to treat this as a massive technological stack, one that needs to be solved layer by layer. And the engineering hurdles, they are absolutely immense. First, we're going to need gigawatt-scale, long-duration energy systems that are leagues beyond anything we can currently build. We'll need incredibly advanced materials, shells capable of handling ultra-high stresses. We need laboratory-scale instruments that are sensitive enough to detect minute space-time curvature just sitting on a benchtop. And importantly, we still need theoretical closure on exactly how to keep the warp bubble stable while it's actually in flight. Because of these incredibly tall hurdles, realistically, we are looking at a timeline that spans centuries. In the 21st century, right now, we are securing the mathematical proofs. Then, moving into the 22nd century, we might actually start seeing those benchtop curvature tests. The 23rd century could potentially bring uncrewed orbital tests. And by the 24th century, perhaps we finally achieve that dream of reaching Mars in a matter of days. So yes, Proxima Centauri is still incredibly far off, but these incremental milestones, they are firmly grounded in actual ongoing research programs today. All of this leaves us with a pretty incredible question to ponder. When will humanity finally cross that 25 trillion mile gap? The physics permitted, the math is actively clearing the way as we speak. And honestly, as a species that has walked on the moon and can detect the gravitational waves of black holes colliding billions of light years away, we simply don't give up on a problem just because the numbers look hard. The ultimate voyage is still being planned, literally one equation at a time. Thank you so much for joining me on this explainer. So what impossible physics will we conquer next?